Here's another video for the lecture intropde. In this video we present section 5.3, and in this section we give the solution of the wave equation, of the homogeneous wave equation in dimension 3. In the last section we derived the Euler-Poisson-Darboux equation. And now we solve this Euler-Poisson-Darboux equation. So let's recall this equation and then see how it looks like in dimension 3. So n is now 3. N is 3. And then we obtain, here is the Euler-Darboux-Poisson equation in lemma 5.2. So we have du quad, the second derivative with respect to time, x, r, and t, minus the second derivative with respect to r of x, r, and t, and finally minus, now n is 3, then we have 2 over r of du by dr of x, r, and t is 0, and of course we have the initial values. U of x, r, 0 is g of x, r, and du by dt of x, r, and 0 is h of x and r. Yeah, this is now the initial value problem which we have to solve. Yeah, initial value problem for the spherical means. Spherical means in dimension n equals 3. Okay, and now we see how we can solve this. Yeah, we will later see that in all odd dimensions we can transform this to the one-dimensional wave equation, but not in even. This is the reason why we first solve the three-dimensional case before we, in the next section, give the solution of the two-dimensional case. So now we make a substitution. U tilde is just u of x, r, and t. Yeah, then now what is if we take the second derivative, d square of d r square of u tilde. Okay, here I should write u tilde of x, r, and t. Now the second derivative is, of course, the first derivative is d by dr, and then we have u of x, r, t plus r times du of d r from x, r, t. Okay, and now do the second derivative. Yeah, then we get two terms. So we get 2 times du by dr from x, r, t. And here we get, as the second derivative, we only get one term, r plus du by dr of x, r, and t. Okay, and if we rewrite this here, yeah, then we see we get exactly, if we divide now by r, then we get exactly this equation here, this equation. Yeah, so this is, so this shows, yeah, this now shows that du that d square by dt square of u tilde of x, r, and t minus d square by dr square of u tilde of x, r, and t. Yeah, this is exactly this times r. Yeah, this is r times, okay, and then we get d square u d square r x r t minus, now we use sorry, here was missing dr square. So then we get this term, but we put an extra r outside, so we have minus 2 over r du by dr of x r t, and minus, here we put r outside, so we get du square by dr square of x r and t, and this is 0, yeah, due to the Euler-Poisson-Darboux equation. Yeah, and of course we have u tilde of x r t is equal, at 0, yeah, the initial value at 0, this is clearly g tilde of x r, and the derivative by dt of u tilde x r and t is h tilde of x and r, where we define, clearly we define g tilde of x and r. This should be an r, not an t. This is clearly r times g of x r, and h tilde of x and r is clearly r times h of x and r. Okay, and in addition, yeah, since we have multiplied with r, yeah, so we have in addition that u tilde of x, and if r is 0, yeah, and t, this is 0, yeah, by this extra factor r, yeah, for all x and t are free cross r plus 0. Okay, now this initial value problem we already solved. Yeah, this is exactly the reason why we solved this in the first section. Yeah, so we solved this initial value problem in the first section. Yeah, and here is here is the solution. Yeah, okay, and what is the solution? So this is the solution. So we obtain u tilde of x and r and t is equal to now we are only interested in r smaller. So x, this x here is of course here the r. We are only interested in this situation. Yeah. So we assume as a for r smaller, or okay, we will see in a moment why we are only interested in this situation. Okay, then we get 1/2 of g tilde of x, and now we should insert t plus r, minus g tilde of x and t minus r, and plus this integral 1/2 integral of t minus x, t plus x, h tilde of x and y dy. Yeah, okay, so this is the formula for which now we inserted our formula. Okay, we call this here, we call this S. Yeah. So this is exactly this formula here. Now, now we use continuity, and of course we are interested in u of x and t. Yeah, also by continuity, we clearly have that u of x and t is the limit r going to 0 of u of x and r and t. R going to 0, and this is clearly limit r going to 0 of u tilde of x and r and t divided by r. By definition, u tilde was u times r, so we have this. Yeah, and since this is the mean, yeah, this we had several times before, the mean over very small balls converges if the radius goes to 0 to the value at the center, and x is the center, so we exactly have this equation. So now we can calculate. Let's insert this. Now we obtain our formula for our solution. R going to 0, okay, 1/2, and then we have g tilde of x t plus r minus g tilde of x t minus r x t minus r divided by r plus limit r going to 0. And now we have this other term, limit 1 over 2r integral from t minus r to t plus r h tilde of x y dy. Okay, here this is clearly, also now we see that this is the derivative. Okay, how we see this? So let's first rewrite the first term. R going to 0, 1/2. Now we just add g of x t plus r minus g tilde of x and t divided by r, and then we also add plus g of x and t minus g of x and t minus r divided by r. Okay, this, let me rewrite it, that you can read it. So this is 1/2. Now we have g tilde of x t plus r minus g tilde of x t plus g tilde of x t minus g tilde of x comma t minus r, and divided by r. And of course this term here, 2r, is exactly the length of this interval. So it is the mean value on this ball. Yeah. So in the limit, this is just the value when we insert y equal to t. So here we have, here we have exactly h tilde of xt. Okay, now let's do now let's calculate this limit. Yeah, this is of course twice the derivative. So, and 1/2. So we get d by dt of d tilde of xt plus h tilde of xt. Yeah, so this is our solution here. Okay, now let's insert the formulas for g tilde and for h tilde. So this is d by dt of t times mean value of g of y dy integrated over the ball with radius t. For the radius we now insert t, and plus integral over t, mean value of t. Now the t we can put outside. So plus t mean value of h of y d sigma of y over the boundary here. Sorry, this has to be the boundary. So this, now let's here calculate this derivative. Yeah, and to calculate the derivative, we should of course again transform this such that the domain doesn't depend on t. So we transform this into the unique ball 0, 1, and then we have to clearly x plus t y. And this term we just leave as it is. And this has nice form. Okay, and here now we can calculate the derivative. Now we can go inside. We get two terms. Yeah, we get two terms. So we combine it with this term. No, first not. Also we get here, we get this term, g of x plus ty, plus, and now if we take the derivative, we get t, sorry, of course, mean. And taking the derivative, this gives inner derivative is y, and outer derivative is the gradient. Gradient of x plus ty times y times d integrated on this boundary, plus of course this term t x t h of y d sigma of y. Okay, and now we transform back. Yeah, and then we combine these two terms. So we get this integral xt. And then we have clearly t times h of y plus g of y. And the whole thing integrated over this ball. Plus, and for the second term, now we can right now put this t inside, then this is ty, and then transform back. And ty, we of course may write as this g of y times y minus x d sigma of y. Now, okay, to make this clear, maybe we call this here set. Yeah, we call this set. This is better. And then here again we call this set, and here also. So we have set d sigma of set, and then we clearly have, also if y is equal to x plus t set, then t set is equal to y minus x. Yeah, for this reason we have here this, and here is missing the gradient. Yeah, and this gives now this formula. Yeah, okay. Here the t, this here's missing the set. Yeah, this t we put inside and combine it to t set, then we have t set is y minus x. Yeah, so this is this term, and of course the mean integral doesn't change if you take the same function. Okay, so this is now Kirchhoff's formula. Kirchhoff's formula for the homogeneous wave equation in dimension 3. Yeah, okay. What we did today, we considered the special case of dimension 3. We made a simple transformation just by multiplying our functions and initial values, also the spherical means, with r, and then we see this transforms it just to the one-dimensional wave equation. And clearly we have that this u tilde is 0, yeah, on this boundary of the positive numbers, and for this reason we end up with the initial value problem of the one-dimensional space wave equation, which we already solved. We insert this solution, and then we get Kirchhoff's formula.